Here's a summary of some of the information from the example I showed in the last video. I had a standard form of a linear equation, x plus 2y equals 7. We showed that the slope was negative 1/2, and I found 3 points that actually satisfy or solve the equation, and we plotted them, got a graph. Now, a couple things that are very interesting about this. The slope here is negative, and I mentioned in the video that a negative slope tells you that you have a rise that goes down, a drop technically. So a rise that goes down and a run that goes to the right. And that's what gives us this decreasing graph, okay? So when a slope is negative, that's always going to be the case. It's going to imply a negative rise and a positive run. They're going to be opposite sign. Okay, or you could think of it as a positive rise with a negative run going the other way, but that would give you the same sort of graph, same shape, right? So negative rise, positive run, or positive rise, negative run gives you the same downward slope to the right. Okay, so if the slope is negative, you have a decreasing, or is decreasing to the right, okay, always. If your slope is positive, you end up with a graph that's increasing to the right. Okay, that kind of makes sense. If your slope is positive, you have a rise that's positive and a run that's positive, so they're going up and right. Or you could think of it as a rise that's negative and a run that's negative, and their ratio, the negatives cancel out, and you still get a positive slope. So either way you look at it, you get this going up to the right. So a positive slope gives you an increase to the right. Okay. Now, there are two other types of slopes that are a little bit weird, and that's because either the rise or the run is 0. In the case that the rise is 0, a rise of 0 gives you what we call a horizontal line, because the graph, no matter how far you run, the graph is not changing vertically. So you have a 0 rise and whatever you want for the run. 0 over anything is 0, and so that gives you a 0 slope, okay? So a slope of 0 gives you a horizontal line. And so just a little sketch here. So if your graph is increasing to the right, graph is decreasing to the right, and the graph is horizontal. So those are the 3 situations. And technically, these are the only 3 situations that you can have for a function. There's some definition details in there that I'm not going to get into, but there is one other option, and it's a weird one, and it's kind of an exception to some of these. It's where the slope is undefined. Undefined slopes occur when the run is 0, right? So if you had a fraction and you were dividing by 0, we can't do that. Division by 0 is undefined. There's no such number that is something divided by 0. And so if your run is 0, that means your graph is going up, but it's not going over. Okay, it's going straight up or straight down. No run at all. That's going to give you an undefined slope. And so that occurs with a vertical line. So slopes that are undefined are vertical, or have vertical lines. Okay, ones that go straight up and down. Okay, so that gives you just an overall summary of what the slope can tell you. Now, what's interesting about this standard form is that if I solve it for y, if I were to take that equation right there and I get the y by itself, how do I do that? Well, I use properties of equality. I can add the same amount to both sides, subtract the same amount, divide, whatever, multiply, as long as it's the same amount to both sides. And so if I want to get the y by itself, I have to get rid of the x. I have to zero that out. So I'm going to subtract x from both sides of this equation. Get 2y equals, I'm going to write it as negative x plus 7. These are unlike terms, so I cannot combine them. And then I'm going to divide out the 2. All right, divide both sides by 2. When I divide both sides by 2, and remember you have to do this on both sides of the equation, I'm going to actually distribute that. Division can distribute, and it's going to distribute to both terms on the top. Here they cancel, So I get y is equal to negative, this is 1/2 x. X over 2 is the same as 1/2 x. Doesn't matter how you write that fraction. Plus 7 over 2. Okay? And so here, what's very interesting is that there are some features of the graph that show up in this equation when y is by itself. Particularly the slope. That's a big one. Right here is our slope. Notice that negative 1/2 corresponds to the m that we found earlier. That's not a coincidence. That's always going to happen. It can be proven. I'm not going to derive that or prove that in this video, but I do have other videos if you're interested in seeing that, where that slope is derived. If you're interested in those details, email me and I can send you a link to those videos for other classes, but you know, it's kind of interesting. Anyway, I'm sure I'll get a flood of emails after that. Joking. So anyway, negative 1/2 is our slope. Now this other number here, the 7/2 is interesting because 7/2 is 3.5. Right, 3.5. And on this graph, you might notice that there's a point here where the graph goes through the y-axis and it appears to be somewhere between 3 and 4. I don't know if you can see that. I have that written very small, but it is. In fact, it is actually 3.5. And this number, the constant, is always going to be the y-intercept. A y-intercept is the point where the graph crosses the y-axis. And that's kind of interesting. That also can be proven to happen every time. It's not a coincidence for this particular example. If I were to look for or identify the x and y intercepts on this graph, there's a particular way to do that. Here I already have the x-intercept. I've solved for that. I didn't really specify this in the previous video when I came up with that point, but to find an x-intercept, remember by definition an x-intercept is where the graph crosses the x-axis, and then we'll talk about the y in a minute. Where it crosses the x-axis, that point, no matter where it is on the x-axis, the height of that point is 0, which means the y value is 0. Okay. So at the x-intercept, the y value is always 0. If you then plug that 0 into the original equation, x plus 2 times 0 equals 7, the 2 times 0 is 0. It isn't necessary, it drops out. And x is equal to 7. That's where we get our x-intercept from in this case. The y-intercept is found in a similar way. With a y-intercept, and I'll abbreviate intercept with int, I do that a lot. With a y-intercept, it's the horizontal position that's still at 0. Okay, you haven't moved horizontally from the origin, but vertically you do. And so the horizontal movement of 0 tells you that x is 0. The coordinates of that point are going to be 0, something. We want to find out what that something is. So we plug the 0 into our equation. 0 plus 2y equals 7. Obviously the 0 is unnecessary. And so we just have 2y equals 7. You divide by the 2. And you could write it as 7/2 or 3.5. Either way. Okay? If I was plotting this on a graph, which I am, I would write it as 3.5 because I can identify that on a number line easier than 7/2. But if I'm using it in an equation like this, 7/2 is just fine. All right? And so the corresponding ordered pairs then are 0, 3.5. And for the x-intercept, which I forgot to write down, but you kind of already have it, it's 7, 0. All right? So in every case, if you get y by itself in a linear equation, the slope will always be multiplying the x, and the y-intercept will always be the constant. Again, this can be proven to work in every situation, not a coincidence on this one. And so we have something called the slope-intercept form. Slope-intercept form of a line has the y by itself, followed by an mx plus b, m being the slope times x, plus b B being the y-intercept, okay? We often use the variables, the x-intercept is a comma 0, and the y-intercept we typically call 0 comma b. So b being the y-intercept, all right? So you have the slope and the y-intercept on the slope-intercept line, okay? Or form of line. Okay, then we have another form. This one I'm not really going to get into in this video. It's not really necessary for what we're going to be doing, called the point slope form. It allows you to find the equation of a line if you're just given a point and a slope, rather than 2 points or rather than any other information. Again, I'm not really going to get into that because we don't need it, but it is another form of a line that can be useful for certain applications. What we're really going to be dealing with is the slope-intercept form so that we can graph lines, and the standard form. Standard form is very nice for getting y or x and y intercepts. The slope-intercept form is nice for getting the slope and the y-intercept, okay? So that being said, just to give a couple quick examples here, get rid of some of this. And if I were to have, let's say, an equation like 5x plus 10y is equal to 8, for instance. If I solve that for y, I can get the slope and the y-intercept pretty quickly, right? So solve for y, you subtract off the 5x from both sides. Again, these are unlike terms. 10y is negative 5x plus 8. Typically we write the x term first because then it will match with this formula. That's all. It doesn't matter if I could do 8 minus 5x if I wanted to, but I don't want to. So we'll divide then by 10, and I'm dividing both sides by 10, but again it distributes to each term on the right. And so what I'm left with is y equals negative 5/10 times x. 5/10 is 1/2. So that reduces to negative 1/2 x, and then 8/10 reduces to 4/5. Always reduce our fractions. You could write this as a decimal, but the decimals aren't very useful, except maybe the 4/5 would be kind of nice. That's 0.8, 8/10, 0.8. You can do negative 0.5 x plus 0.8, that would be valid, although a slope of 0.5 is harder to work with than a slope of 1/2. So the slopes are often nice as a fraction, and the y-intercepts are often nice as a decimal. It doesn't really matter which form you put it in, you just want to be able to use the numbers, okay? So if I was to plot this graph, I would start at 0.8, which is the y-intercept, right? 0.8 is a little bit below 1, and then my slope is negative 1/2, negative 0.5. So negative 1 over 2 means if I drop 1, I have to run 2. So if I drop 1 unit, that would put me at negative 0.2. Think about that. So subtract 1 off of this, and you get to negative 0.2, and run 2 units over. All right. So that would give me a point. This is kind of weird. It gives me a point there at 2 comma negative 0.2. That would be my second point, and then I could draw the line through them. It works. Kind of a sloppy example, but it works.